In this video, we're going to talk about the transformation of a single random variable. And in particular, that variable is going to be continuous. So let's go through some of the setup here, which is going to involve a review of some concepts for continuous random variables. So let's suppose that we have got a continuous variable x with known density function f sub x of x. And that's a notation here if you have more than one variable going on, to have the density functions identified for each variable by a subscript. So for example, if we had a continuous random variable y as well, we might write its density function f sub y of y so that we can identify it or distinguish it from the density function for x. So we know that probabilities can be calculated for x using the density function directly by integrating, right? So we can do the probability that a is less than or equal to x is less than or equal to b. That's the area under the density curve, or it's the integral from a to b of f sub x of x dx. We also have the opportunity or the option of computing the cumulative distribution function first and using it to calculate probabilities. So by definition, the cumulative distribution function is the probability that x is less than or equal to small x, that is capital F sub x of x, and that is defined as the integral from minus infinity to x of f, the density function, f sub x of u du. And if we recognize this format from the fundamental theorem of calculus, the fundamental theorem of calculus tells us that this is an antiderivative, derivative, so that the CDF is an antiderivative, of the PDF. Right? The cumulative is an antiderivative of the density. And then we can calculate the probabilities for x by using the CDF, right? So the integration has been done once and for all, and we can do f sub x of b minus f sub x of a to calculate that same probability as we would have done up here. Now, however, if we have another random variable, if t, right? If t is a function, which means a transformation of x, if t is a function of x, then it itself is a random variable. So if t is g of x, if t is a random variable, then it also has a density function, and probabilities can be calculated for t. However, if we don't know t, all we know is x, and that, x is density function that we have, and we know this function g. That is still not enough to give us necessarily the density function for t. It can be very difficult to calculate the density function and hence probabilities for t. However, what we're going to do is look at one situation in particular where it is possible to obtain the density function for t. And if it's possible to obtain the density function for t, it's possible to calculate probabilities for t. It should be noted, however, that if all that we are interested in for t is the expected value or the variance or anything else that's moment related, then this theorem, LOTUS, which is the law of the unconscious statistician, allows us to calculate expected value and other such measures directly from the density function of x. Right? So expected values, variance, that sort of thing, can be calculated by this theorem, and this is the theorem of LOTUS. And so that says the expected value of t, we're remembering that t is g of x. So if we plug in the function g inside the integral, and we integrate from minus infinity of g times the density function, we will in fact get the expected value of t. Why unconscious? Right? Because this seems like a perfectly reasonable thing to do. Well, it is kind of reasonable, but it is quite a deep theorem, and you might sort of not realize that you can't calculate probabilities for t using the density of x. You can calculate the expected value, but you cannot calculate probabilities. So that's in general. In one or a couple specific cases, it is possible. And so that's what we're going to look at now. How does one go about obtaining the density function for t if we know that t is a function of a density of a random variable x, and we know the information for x? So let's look at this situation. Let's let x be a continuous random variable with density function f sub x of x and CDF big F of sub x of x, which, as we said above, means two things. One, the density function here, it gives us the probability that big X is less than some small value x. And since big F, the CDF, is an antiderivative, the derivative of the CDF gives us the PDF. Okay? Now, let's also let t be some function g of x. So t is another random variable that depends on x. And we're going to specify that g in this case needs to be a monotonic increasing function. So monotonic means it does not change direction, and increasing, well, it's only going up. That, in turn, ensures two other properties. It ensures that g is invertible, so that g inverse exists, and it ensures that g plays nicely with inequalities, so that if g of a is less than or equal to b, then I can take the inverse on both sides and maintain the inequality so that a is less than or equal to g inverse of b. So this is our setup. This is our setup with the conditions that ensure this information in red. So if we are looking to find the density function of t, well, what we are going to start with first is finding the CDF for t. So f sub t of t is the cumulative distribution function for t. And by definition, right, by definition, the cumulative density function f sub t of t is the probability that the random variable t is less than some value small t. Well, if t is g of x, right? That is our setup. So that gives us the probability that g of x is less than t, right? Because t is equal to g of x. So that tells us here, right, one of the properties that we wanted on this side was that we could use the inverse to solve. We could use the inverse to solve with an inequality. So x is less than g inverse of t, which is exactly the setup for the CDF. F sub x of x is exactly the probability that x is less than some small value x. So our small value x here is g inverse of t. So that gives us the CDF of x evaluated at g inverse of t. So f sub x of g inverse of t. That was the CDF for t. That would let us calculate probabilities for t. But if we wanted to go further, if we wanted to find the density, the PDF for t, right? So f sub t of t, little f, the density function. Well, we had one more relationship. The CDF is an antiderivative of the PDF, so we can differentiate. So the f sub t of t, the density function for our new random variable t, is the derivative of its CDF. And its CDF, right, its CDF up here, we just solved for. So its CDF we can replace by f sub x evaluated at g inverse of t. Then what do we do? We do a chain rule. So that gives me the derivative of big F evaluated at the inside function times the derivative of the inside function. Oh, but wait, there is more. The derivative of x's CDF is x's PDF. So f sub x, that's the density of x, evaluated at g inverse of t times g inverse of t prime. So that is the method. That is a formula, but honestly, I never use that formula. I use the process every time to figure out what's going on. So let me show you that in an example. So, example here. Let's imagine that we have the time t, that a manufacturing system is out of operation, has a CDF, So the F, right, in my notation of above, I would call this F sub t of t. Right, that is the CDF of our variable t. Now, t is the variable that we know, right? So it is playing the role of x above, right? This now is asking us to calculate the resulting cost to the company is y. Y is a function of t. Y is a function of t. Now this notation is all mixing up the notation that I used before. G is now going to be the density function for y, and they want g of y for y greater than 4. Right? So that means that I'm not going to use g like we used above. I'm going to use g as the density function here. And anyway, I'm just going to run through the process. So the formula for my g's and my t's and my whatever doesn't matter. I'm just going to run through the same process and calculate the answer. So if little g is the density, I'm going to let big G of y be the CDF, right? The CDF, and that is going to be an antiderivative. By definition, this is what the CDF gives us. The CDF gives us, g of y, gives us the probability that y is less than or equal to some value y. Well, y is t squared. So that is the probability that t squared is less than y. Now we have to be careful because the square function, right, the square function here is not monotonic. It is decreasing and then increasing. But we are told that y is greater than 4 and t is greater than 2. And so if we are looking at only on that part, right, if y is greater than 4 and t is greater than 2, well, I don't know, let's imagine that it is some value here, 2, and so we are actually only looking at this part of the function, and that part of the function is indeed monotonic. It is only going in one direction, and it is increasing. It is monotonic and it is increasing. And so I can forget about the other side, and I can use this inequality, right? That if t squared is greater than y, that's not it, less than y, then t is less than root y. It is like using the inverse function. So we are using the inverse function on a piece of the domain where the function is indeed monotonic and increasing. So we get here from p is equal to the probability that t squared is less than y, we can say that is the same as the probability that t is less than root y using this logic over here. That is, by definition, that is the definition of what it means to use the CDF for t. That is f sub t of root y. So that means I can plug root y into this function. So that is the 1 minus 2 over root y, right? I'm plugging root y in for t here, which gives me this function here, 1 minus 4 over y. Now that is the CDF, and if that's what we were asked for, we would stop. But we are not. We are asked for the density function. So we have one more step left to do, and that is differentiate. The density function g of y is big G prime of y. So I take the derivative of the expression that I got above here, and using your differentiation rules, you should see that you get 4 over y squared, and that is our final answer. That is the density function of our new variable y.